You are live. Hello, everybody. Welcome to John Chappell Natural Philosophy Society. I'm just looking on my YouTube link here to see if I'm turning up on that. Yep, I'm on there. Hopefully, the sound's coming through on it. And I'll go to the advertising now about please donate money to John Chappell Natural Philosophy Society from David DeHilster.
Hello, my name is David DeHilster, and I'm president of the John Chappell Natural Philosophy Society. Our organization is unique in the world in that we allow for serious criticisms of mainstream science, from physics to cosmology and from math to philosophy. And today, this organization resides 100% online. If you enjoy our Saturday morning talks, our websites, and the community of amazing critical thinkers you can interact with on the internet, then please consider contributing to our annual fund drive. It costs almost $3,000 per year to keep our internet presence and our Saturday morning talks alive and well. I want to thank all of our members who pay monthly and annual memberships, which is vital to our day-to-day operations. But unfortunately, this is not enough, and that's why we're looking to raise $2,000 in our 2024 drive. So if you don't want this organization to disappear, and you think that its mission is important, then please consider donating to the CNPS. It's vital to keeping science moving forward. Please go to fund.naturalphilosophy.org and donate today. Thanks once again from all of us at the CNPS. Your donation is vital.
Hello, everybody, and welcome back to another exciting session on special relativity. We're complaining about special relativity. Special relativity is a big subject, a lot of things, involves lots of things, and so we're on the issue of space time. And so the discussion will be opened up what about space time as to whether we need it or not. So let's try putting the slides on. And so the question today is, should space time be discarded? Let me get on to the next slide. So this session is sort of a carry on from the previous one about Minkowski space time. And the question this time being asked is, should space time be discarded? I.e., was it a bad idea to add space time to physics? Question mark. Adding space time to physics theorizing has created all sorts of problems. As is known, there's a problems unifying Einstein's relativity with quantum physics. One proposal to unify physics is to discard space time. So whatever benefits you think space time are, it could be looked upon as causing problems with trying to unify relativity with quantum physics. And as per the last session, did adding Minkowski space time to Einstein's relativity turn it into a different theory? That was the question asked last time. So, recapping from last session, Einstein 1905 did his special relativity paper on the electrodynamics of moving bodies. Then after that, space-time got added. And in 1915 came general relativity. So between 1905 and 1915, Einstein was struggling to extend stroke develop special relativity to a more general theory. During that time period, Minkowski space-time got added to it. And so some people can think, oh, putting the space-time idea into relativity was a mistake. So this is the example from last time. It's Alexander Utzinger and he was thinking things went wrong in that development period between 1905 and 1915, and he's got a lot of videos on that and a lot of papers, and he has books on it and so forth. So it's more he goes into a lot more details than what we did last session. In this session, I'm going to show two videos. And the second video I'm going to show is this one. And he's given a talk and he's saying the doom of space-time. Basically, he thinks space-time should be discarded from physics. So as I pointed out, it's a problem trying to combine relativity to quantum physics, and space-time is one of the areas that messes up trying to unify these two things together. I think one of the issues is if I have space-time, the next want to curve it and have that curvature representing gravity, because initially it's called flat space-time, and that's in the context of special relativity. And then in the further stages of development of relativity to become general relativity, they start thinking in terms of curving space-time. And in the context of general relativity, a lot of people start thinking there is no gravitational force, and instead it's space-time curvature. And if you go to quantum physics, it's not thinking of forces in terms of space-time curvature. So that is messing up the idea of trying to unify forces. But first, before the video called Doom of Space-Time, I want to look at Sabine's video. And this is Sabine's video I'm going to show. Is gravity a force? And that's the problem which happens with general relativity. Do you stop thinking of thinking of gravity as a force, and instead start thinking it as space-time curvature? And us dissidents who disagree with relativity, well, that's probably one of the areas we start disagreeing with relativity about. But of course, relativity is a big subject, and we can find lots of different things in relativity to start complaining about. So this complaining about space-time is just one of those issues. So both Sabine and the other person, Arkani Hamed, I would consider as mainstream physicists. Sabine seems to think that relativity has brought in the idea that space-time curvature has replaced the Newtonian idea of force ? If we're back to treating gravity as Newtonian force, it'd be a lot easier to deal with quantum physics, because quantum physics already is dealing with other forces. And in the case of Hamed, he seems to be thinking along the lines of at least some parts of relativity is wrong. So this is pointing out that even in the mainstream, there are people who don't think relativity is quite right. And the example being this session is Hamed, because he's thinking of space-time as being the problem in unifying physics. So the first video I want to show is Sabine, that highlights the mess. In my opinion, I consider the mess being made of force in the context of general relativity. And she's thinking of gravity as space-time curvature. So I want to bring her short video up to let her explain her point of view, which I don't necessarily agree with. Here we go. Here comes Sabine's video.
Days, which brings up the question, what is weight? Weight is actually the force that acts on your body due to the pull of gravity. Now, the gravitational force depends on the mass of the object that is generating the force, in this case, planet Earth. So you can lose weight by simply moving to the moon. Technically, therefore, I should have said I lost mass, not weight. Why do we normally not make this distinction? That's because in practice it doesn't matter. Mass is just a number, a scalar, as physicists say, but weight, since it is a force, has a direction. So if you wanted to be very annoying, very accurate, then whenever you'd refer to weight, you'd have to say which direction you're talking about. The weight in east direction, the weight in north direction. Why doesn't anyone ever mention this? We don't usually mention a direction when we talk about weight because we all agree that we mean the force pulling down. And since we all know what we're talking about, we treat weight as if it was a scalar, omitting the direction. Moreover, the gravitational attraction downwards is pretty much the same everywhere on our planet, which means it is unnecessary to distinguish between weight and mass in everyday life. Technically, it's correct. Mass and weight are not the same thing. Practically, the difference doesn't matter. But wait, didn't Einstein say that gravity is not a force to begin with? Ah, yeah, there's that. Einstein's theory of general relativity tells us that the effect we call gravity is different from normal forces. In general relativity, space and time are not flat like a sheet of paper, but curved, like the often named rubber sheet. This curvature is caused by all types of mass and energy, and the motion of mass and energy is in return affected by the curvature. This gives you a self-consistent closed set of equations known as Einstein's field equations. In Einstein's theory, then, there is no force acting on masses. The masses are just navigating the curved spacetime. We cannot see the curvature directly, we can only see its effects, and those effects are what we call gravity. Now, Einstein's theory of general relativity rests on the equivalence principle. The equivalence principle says that locally the effects of gravity are the same as the effects of acceleration in flat space. Locally here roughly means nearby, and acceleration in flat space is described by Einstein's theory of special relativity. So with the equivalence principle, you can generalize special relativity to general relativity. Special relativity is the special case in which space-time is flat and there's no gravity. The equivalence principle was well illustrated by Einstein himself. He said, let us consider you are in an elevator that is being pulled up at constant acceleration. There's one force acting on you, which is the floor pushing up. Now, Einstein says, gravity has the very same effect without something pulling up the elevator. And again, there's only one force acting on you, which is the floor pushing up. If there was nothing pulling the elevator, so if there was no acceleration, you would feel no force at all. In general relativity, this corresponds to freely falling in a gravitational field. That's the key point of Einstein's insight. If you freely fall, there's no force acting on you. And in that, Einstein and Newton differ. Newton would say if you jump off a roof, the force of gravity is pulling you down. Einstein says, nope, if you jump off a roof, you take away the force that was pushing you up. Again, however, the distinction between the two cases is rather technical and one we do not have to bother with in daily life. That is because in daily life, we do not need to use the full-blown apparatus of general relativity. Newton's theory works just fine for all practical purposes, unless possibly you plan to visit a black hole. Thanks for watching. See you next week.
Right. Hello. So that was Sabine's talk on the question, is gravity a force? And I don't necessarily agree with everything she says, but it seems to be the point of view of various people in the mainstream to think of things in that way, that gravity is space-time curvature, and that's sort of like an extension of starting with flat space-time and then curving it. So in my view, space-time is messing things up from that sort of direction. So we'll go on to the next video. If you give me a second now to bring that up. No. Oh, God. We move. Oh. Okay, I've got to bring up this other video. Stop screen. Aha, right. Share screen. And go for that one. Share. Launch. Press and launch. Right, so this is the next video, and it's a very long video, and so I'm only going to show half an hour of it, which I think is the relevant bit where he explains why he thinks space-time is doomed, meaning doomed as why you should discard it. So we'll just start this video up now. So go.
Too loud? Is that okay? Is that okay? All right. So it's absolutely wonderful to be here in this beautiful setting. We're going to be enjoying some light after dinner entertainment with the subject of the doom of space and time. Let me just say a few things. Oh, I shouldn't start yet?
I think we're going to trade mic.
Oh, we're going to trade mic.
Your mic sounds horrible.
Sorry. I may have put it on wrong. Oh, it's okay.
It's a little-
Is that better?
That's not quite right. There we go. Let's see.
Is that okay?
Yeah, I think.
All right, fine. So let's do this. Now we're going to get it hopelessly entangled.
Well, that's-
Now we're going to see what's in my pocket. Actually, I don't want to do that. You know, cat pictures.
This is
You
an
know that.
experiment in entanglement.
There we go. There we go. Okay. Ha. That's why you get paid the big bucks. There we go. All right. Is that better? Okay. So first, just a few words to put things in a little bit of context. Fundamental physics is the oldest and most mature part of science, depending on where you start counting. Our field is 2,000 years old or 400 years old, really, in its more modern incarnation, starting with Kepler and Galileo and Newton. We understand the way things work really well now. Okay, our understanding of the structure of the basic physical laws of nature, especially after the revolutions of relativity and quantum mechanics in the early part of the 20th century, is absolutely spectacular. 100 years ago, it's amazing that human beings could walk around on the planet and not know the answer to questions like why is water wet and why is grass green. Okay, we have answers to all such questions now. Really, everything about the sort of basic structure of the world around us are beautifully understood in the context of these two great principles, the two great revolutionary principles of 20th century physics, quantum mechanics and relativity. Really quantum mechanics and Einstein's picture of space and time. Now, beyond that, we do more esoteric things. We want to test the way these laws work. We can make predictions for things like the magnetic properties of electrons, where we can, in some happy circumstances, we can do theoretical calculations of 12 decimal places. And our experimental friends can make an experimental measurement to 12 decimal places, and they agree to 12 decimal places. Okay, so we have this absolutely spectacular theoretical structure and understanding of the basic laws of nature, and that's why most of the developments in most of science, certainly, but also even in this part of science, should not have the character of pulling the rug out from under you. Okay, because things work amazingly well, right? And that's why only every century or so, on that kind of time scale, do you run into a situation where you suspect something very big is wrong, and indeed you do have to pull the rug out from under yourself. And something that seemed like an absolutely, completely obvious, hardwired into the way we think about the universe thing has got to go and has to be replaced in some totally shocking way by more primitive, more alien principles and ideas. That's the kind of place we are in our field today. Okay, and there's a number of different problems that I could say this about, and I'm focusing on this one that has to do with the end of space-time. There's one or two other problems of this rough character, but I'm going to split. So I'm going to try to do something very dangerous in this talk. Whenever talking about fundamental physics or theoretical physics to even a slightly general audience, and this isn't a perfectly general audience, of course, I understand, but even so, there's always a temptation to lapse into metaphor and simile in order to explain concepts that can't really be explained in that way. They have to be ultimately understood in more precise mathematical terms. That's perfectly fine. I've done it myself on more than one occasion. I'm sort of sick of doing it, though. And what I'm going to try to do in this talk is tell you the very dangerous thing is I'm going to try to tell you true things. Okay, so everything I'm going to tell you is going to be true and accurate. Some of them will be purely with words, so you will have to think about them hard. Okay, so not everything I'm going to say will be completely obvious, but everything will be correct. And if you don't understand everything in real time, just remember the words and just know that they're true. And so, and that's actually, that'll be useful, because as you think about it more, you learn more, you think more, you talk to more people, that knowing that thing is true will actually be helpful in your continuing understanding. So in the first part of the talk, I want to explain why space-time is doomed, what the arguments are that we have to get rid of this seemingly fundamental notion. And in the next part of the talk, I'm going to talk about one particular strategy for going about attacking this problem. There are many of them, but the one particular strategy that my friends and I have been pursuing for the past decade or so. And the first part is just, I'm sort of reporting from the front of what my friends and I in this subject have discovered over the last 30 or 40 years. Really, not me, I wasn't around 45 years ago, but anyway, the things that we've learned that we've collectively learned that set the stage. I like to describe where we've gotten to as the last 4 centuries have been like trekking through Nepal. You land in Kathmandu, you get some Sherpas, you go, there are these complicated hills, you do all these things, and eventually, finally you get to base camp at Mount Everest, and there it is. There's the summit. It's sitting there, and you have no choice but to start going up. Okay, so the first part of the talk is to get you to base camp. Okay, just so you know what it is, what the problem is, why we have to do this crazy thing, and in the second part, I will tell you one particular approach. As I said, there are many others, and but I present it to you as an example A because it's what I'm actually thinking about. So it'll be more personal and fun, but also B as an illustration of the way we go about trying to attack seemingly impossible to solve problems of the sort that I will explain to you in our business, and what the sort of methodology is to try to take very huge scale problems and break them into little chunks that you can do something about when you wake up in the morning. Okay, so that's just summarizing what I said quickly. We had 2 big revolutions in the first third of the 20th century in our understanding of physics. There are the revolutions of Einstein's picture of combining space and time into space-time, and in many ways, much more revolutionary developments of quantum mechanics. Now, these 2 pieces of physics are in principle, even as they were discovered, are sort of separate intellectual frameworks. You could imagine a world that was completely classical, but which had a finite upper speed, and so that world would be relativistic. Or you could imagine a quantum mechanical world that didn't know anything about relativity. So there are sort of 2 different logical frameworks. And so the second those were established, theoretical physicists try to figure out, how do you talk about universes that are compatible with both of these principles at the same time, that have quantum mechanics and relativity at the same time? And that turns out to be an incredibly difficult thing to do. A very, very constrained theoretical structure that's known as quantum field theory. Okay, so now a particular quantum field theory, this famous standard model of particle physics, describes the particular elementary particles and interactions that we see in our universe. But quantum field theory more broadly is a sort of the general rubric in which we could imagine describing any candidate universe that's compatible with these two big principles. I said it's incredibly constraining and incredibly successful. So these 12 decimal place accurate predictions that we make are very subtle calculations that agree with very subtle experiments. These are our principles, the pillars of our understanding are quantum mechanics and space-time. And that's what makes the storm clouds that we have now, the early part of the 21st century, so disturbing, because they're not some little detailed thing here or there that we don't understand, or some particular phenomenon that seems strange that we don't yet have an explanation for. That's par for the course. That's sort of normal science. All the time there's something you're confused about. Otherwise we'd have nothing to do, right? But mostly the things that you're confused about are explained within the basic framework that you have already. You don't have to turn everything upside down in order to deal with them. That's not where we are today. We can at least identify certain kinds of very simple thought experiments, and I'll walk you through some of them, that suggest something very big is wrong, that goes to the very foundations of what makes things so spectacularly successful. That's a paradox. On the one hand, those ideas of space-time and quantum mechanics underlie this, are the pinnacle of the 4 centuries that we've gotten to and work spectacularly well. On the other hand, I'm just about to tell you they've got to go. Okay, and so the challenge is to figure out how can they go, and why, if they have to go, were we faked into thinking they were there? Okay, and that's what I'll talk about in the second part of the talk. Okay, but what are the storm clouds? First, space-time is doomed. That's the title of the lecture, and that's because of the presence of both quantum mechanics and gravity. So I'll explain why that's the case. There's even I didn't put this in the title of the talk because it would have been a little more technical, but in some sense, the second thing I'm saying is more radical. The first thing, all of my friends would agree. The second thing is a slightly more controversial statement, but I certainly believe it, that we're eventually going to come to see even limitations of the ideas of quantum mechanics. I'm not at all saying some crackpot thing like quantum mechanics is wrong or is modified in some crazy way, but that there are situations where quantum mechanics cries uncle. We don't know how to apply the rules to things that where the quantum rules have to be applied to making predictions about entire universes. All right, so let me just say a few things about these 2 points. First, why is space-time doomed? All right, so here's a very simple thought experiment. By the way, I take it many people who give these talks have fancy animation and things like that. I'm a terrible artist, and there's no animation. Okay, so all my pictures are like this. So if this bothers you, maybe we can stop and you can just leave right now. Because it's just going to get worse. Okay, so that up there is a magnifying glass, for example. Okay, that is meant to be a magnifying glass. Anyway, but we're going to do a little thought. What I don't have in is there a laser pointer up here? Okay, fine. Yeah, what I lack in artistic beauty, hopefully, will make up in intellectual content. So here's what we're going to do. We're going to try to look at a region in space and time and just see what's going on there. I want to measure what's going on in some piece of space. And I want to see, can I actually see what's going on at arbitrarily short distances? Okay. Now, a basic fact about quantum mechanics that many of you know is Heisenberg's uncertainty principle. The uncertainty principle tells you that if you want to probe what's going on in shorter and shorter distances and times, you need higher and higher momenta or energies. Okay. That's why the big irony of the LHC, the Large Hadron Collider, is it's a machine that's probing the tiniest distances we've ever probed. Thank you, sir. Thank you. Is the hugest machine we've ever built. Why is that? It's because to go to really tiny distances, we need really gigantic energies. And so we got to build these humongous rings where things are accelerated around and so on. All right, fine. So short distances means high energies. Very good. Now, in principle, there's no limitation to how short a distance you can resolve in that way. By the way, let me just, in order to explain, just to explain that again, if you're literally trying to look to see what's going on at very short distances, you need light whose wavelength is sort of comparable to the size of the thing that you're looking at. And then, because of quantum mechanics, you know that if you have light of a certain frequency, it just has to have a minimum amount of energy. It can't have a tinier energy than that. It has a minimum amount of energy given by Planck's constant multiplied by the frequency of the light. So that's why if you're trying to resolve what's going on at very short distances, you just must have incredibly high energies. Fine. In a world without gravity, there's in principle no limit to the tininess of the distance that you can probe in this way. You can just keep going forever. You just need higher and higher energies. You need to beg larger and larger multinational governments for more and more money, but you, in principle, you can do it. But because of gravity, at some point, something bad happens. What do you think happens? At some point, you're putting so much energy into such a tiny region of space. Now, you know, roughly speaking, E equals mc squared. So like having a lot of energy in some region is like having a lot of mass there. Now, you know, something bad happens when you put a lot of mass in a really tiny region of space. What happens? You eventually make a black hole, okay? And there's so much mass there that even light can't escape from it, okay? So that means that your effort to see what's going on in here eventually makes a black hole that makes it impossible for you to see what's going on in there, right? Now, let's say after that happens, you get frustrated and you build an even bigger accelerator, even higher energies. What happens? Make an even bigger black hole, okay? So this entire idea, in fact, this sort of basic reductionist paradigm that you go to high energies, go to short distance is eventually wrong, okay, because of gravity. There are some distance scale at which it's simply impossible to probe what's going on at distances and times of that order. Now, if you put the numbers in, that's this famous Planck length. It's around 10 to the minus 33 centimeters, okay? It's a minuscule, minuscule scale. Remember, the size of an atom is like 10 to the minus 8 centimeters, okay? The size of a nucleus, proton or a neutron, is 10 to the minus 14 centimeters. The distances that we're probing at the Large Hadron Collider are 10 to the minus 17 centimeters. This is 16 orders of magnitude away from that even, okay? By the way, why is this distance so tiny? That's a reflection of how weak gravity is compared to all the other forces. Okay, gravity is ridiculously, ridiculously weak. But eventually, if you put enough mass in there or enough energy, it becomes strong and it does these terrible things. So we can do this thought experiment that tells us it's simply impossible to give operational meaning to distances and times that are short compared to this famous scale, 10 to the minus 33 centimeters, 10 to the minus 43 seconds, which is how long it takes light to traverse that distance, and so on. Now, every time this has happened to us in physics before, that it's not even in principle possible to give operational meaning to some concept, it means that that concept doesn't really exist. It's something approximate, right? This happened to us with quantum mechanics, with the concept of position and velocity of some particle. That's something that we can talk about in everyday life. We can easily talk about, but we know that quantum mechanics forbids you from knowing precisely what the position and velocity of a particle is at the same time. It's very important in physics to know and think about the things that you can observe in principle with perfect precision, because those should be the objects that your physical theory is about. And here we learn that space and time cannot be those objects, because we cannot actually do any experiments to resolve distances and times with arbitrary precision. All right, now, there's actually a more subtle aspect of this problem. Maybe I'll go over this part a little quickly, although it's quite deep and important. What I just told you might make you think that these difficulties are kind of localized to very short distances, okay? But in fact, it's deeper than that. The difficulty is apparent on all scales, okay? So here's another way of saying the problem, which does not involve a very, very high energies. It involves experiments you and I could do in principle, but very accurate ones, okay? And where, again, we run into, in principle, limitations on what we can observe. Now, this goes back to something having to do with quantum mechanics. Now, a very important fact about quantum mechanics, because the world is quantum mechanical, it's not deterministic. We can only predict probabilities. These are famous facts about, we can only observe probabilities. A theory can only predict probabilities. So What that means is that if you want to get a precise answer in a quantum mechanical world, you have to do some experiment infinitely often, right? You want to verify that the odds of flipping a coin are 50-50. You have to repeat the experiment over and over and over and over again. And in principle, to get a perfect answer, you have to do it infinitely often. That's one infinity. You have to do the experiment infinitely often. There's another infinity that we don't talk about as much in undergraduate courses and so on, but is also important. Quantum mechanics forces you to divide the world into the finite system that you're looking at. But the thing that's looking at it has to be an infinitely large apparatus as well, okay? And the reason is, if it isn't, then the apparatus itself has these sort of quantum jitters and jumps, and so there's an irreducible amount of noise associated with the finite size of the system, so of the apparatus. So let me just give you a concrete example. I am roughly made out of 10 to the 30 things, atoms, very roughly, okay? So let's say I want to measure anything, any quantity you want to name. You know, this famous magnetic moment of the electron that we've measured to 12 decimal places. Let's say I want to measure it to better than that. I want to measure it to 10 to the 30 decimal places. So this is just pause how ridiculous this is, but I want to measure it to, let's say, 10 to the 40 decimal places. I could want to do that. So here I go, graduate students, food, okay. I do the experiment, everything's fine. The 10 to the 10th decimal places, I'm flying, everything's fine. Death, no problem, right? No. But at some point, around the 10 to the 30th decimal place, something very bad happens, because I, as a finite thing, could actually, on that scale, spontaneously fluctuate into a cloud of dust. Okay, that would put a damper on making a precise measurement, figuring out the 10 to the 30th decimal places. One of the less bad things could happen. Maybe my brain could just have a little random quantum mechanical glitch, and even though I should have written down 7 in the 10 to the 30th decimal place, I wrote down 2 instead. Okay, you see, any finite system has an, in principle, error associated, because of quantum mechanics, with any measurement it can make. Now, that error is exponentially small in the number of things that you're made of. That's why it's of practically no significance at all, compared to the first thing that we talked about, where we have to do the experiment over and over again. That's a much more significant source of error. But conceptually, we need to do both things. We have to do the experiment over and over again, and we have to do it with an infinitely large measuring apparatus. And now we have a second problem having to do with gravity. The fancy word associated with it is that there's no local observables. But again, let me give the quasi-practical version of this. Let's say I'm trying to make any measurement of any quantity in this room, okay? And I'm trying to do it. I want to get the answer arbitrarily accurate. So I can't do it. I'm 10 to the 30 things. So I'll make some other apparatus. That other apparatus will get bigger and bigger and bigger, okay? I have to make it bigger and bigger and bigger, but the experiment is happening in this room, right? So if I'm going to fit all that stuff in this room, that apparatus, as I make it have more and more components, bigger and bigger, gets heavier and heavier. And before I make it infinitely big, what happens? It collapses the whole room into a black hole. It's not one of these teeny tiny black holes, but now if you want to measure something with perfect precision, even on humongous scales, still, there's a problem, okay? And by the way, it turns into a black hole. You have another problem, that you can't do the experiment over and over again, because you get sucked into the black hole singularity and die, okay? Inevitably. So that tells you that there is no measurements of any sort in the interior of a region of space and time that can belong as precise properties of the world. Those cannot be the things that laws of physics are about. Okay, that's a very disturbing thing. Not only can't we do the sort of coarse measurements with the big accelerator that makes these black holes, but there's kind of no sort of measurement I can make in some finite regions in space and time that can possibly have any perfect precision associated with them. So these are the deepest reasons we are convinced that space-time has got to be an approximate idea. Now, what can we talk about? There are a few things left that we can talk about, and one of them is the following kind of experiment. What you can do is, we can't do the experiment in finite regions of space and time, so we do experiments that start and end at infinity. So what I can do is take I can take some apparatus, make it bigger and bigger and bigger, but moving further and further apart from other apparatuses. I can use them to shoot some particles in to the interior of the space and time where they bang into each other. All sorts of stuff happens. They come back out, where they're measured in infinitely large apparatuses. Okay, so that's a perfectly reasonable kind of experiment that I can do, and where the results can be, in principle, perfectly accurate, right? So these kind of experiments are called scattering experiments for obvious reasons. The observable that you talk about is a scattering amplitude. The word amplitude there is because it's quantum mechanics. Something different happens every time when you collide two particles. Sometimes two things come out, sometimes three things come out. Everything comes out with some probability. The probability is the square of something called the probability amplitude. So that's the thing that we should be talking about. But the experiments don't happen in the interior of space-time. They start and end at infinity. Now, I've just given you very highfalutin reasons why these scattering amplitudes are interesting quantities, but there's a very practical reason they're of importance to particle physics, is those are the experiments we do. Okay, or very close approximations of those experiments are what we actually do. So, when we collide particles at the Large Hadron Collider, here's a picture of the ground outside Geneva in Switzerland. Of course, you don't see this oval on the ground, but the 100 meters under that oval, 27 kilometers around, there's protons going around one way, protons going around the other way, and they collide with each other. Now, of course, they're not literally coming in from infinity and going out to infinity, but 27 kilometers is plenty big compared to 10 to the minus 14 centimeters, which is the size of these little things. So this is an extremely good approximation to that kind of observable that we're talking about. Okay, so you send some things in, you close your eyes, some things come back out. Of course, in our mind's eye, we think what happened is, well, they went and first this hit that, and then that happened, and something else happened, and then some other stuff came out. But all you really know is what went in and what came out. Okay, and those are the kinds of observables that we can talk about. All right, so that's the reason why space-time is doomed. Now,
Hi. So the video goes on for a lot longer and things get more complicated, but he presented in that little clip the reasons why he thinks space-time is doomed, i.e. you should discard space-time because it's interfering with trying to form a unified theory of physics. It's interfering when you try to unify relativity with quantum physics. So Einstein didn't really come up with the idea of space-time. It came from Minkowski and it got added to relativity. And it's the treating space-time as first flat and then curved. Well, Einstein may be wrong for taking on space-time. So it's still a case maybe Einstein is wrong. Right, so I'm going to open it up to discussion now. So that was the videos to let you have something to think about. Should we get rid of space-time? From the distant movement, we can see too many problems with relativity. So I'm going to try to look down to see what the comments are. A lot of the comments are between people talking among themselves. Come on, show. So Cornelius points out space-time is good mathematical tool, but needs to be applied on all scales as space is continuous, from the universal to the subatomic. Yeah, so space-time does work to a certain extent. It's when you're trying to unify it with quantum physics, you start having problems. So clocks don't run the same at all levels. Well, we're not dealing with clocks this time. So Cornelius points out quantum physics needs to be accepted as an unrealistic attempt to describe everything as particles. Well, quantum physics brings in wave-particle duality, and that complicates things. Okay, but we're not dealing with that bit. We're complaining about space-time at the moment. So trying to move down. Yeah, so a lot of the comments have been people on themselves. Why is it companies that the gravity is so weak? So, why is it commonly said that gravity is so weak? It keeps gigantic planets in check. Yeah, well, gravity is supposed to be weak compared to the other forces, but complaining about the other forces, not going to be dealing with. It's complaining about space time. So, yeah, no. So Andrew says it should be noted that relativity and quantum mechanics have already been unified under quantum field theory. Yeah, Hamed did point out about that, but there are still problems with unifying it, and one of the problems is space-time. Well, Hamed thinks space-time is a problem. So this question is unified how? Well, quantum mechanics deals with particles, wave particle duality, Heisenberg uncertainty principle, and so forth. And relativity deals with relativity principle, equivalence principle, space time, and that sort of thing. So, how do you unify all those sort of things? What prevented them being unified in the first place? Well, it's what they call two different paradigms. You've got the paradigm of relativity as one way of building upon, and the other paradigm is quantum physics. It's another paradigm, and the two paradigms are looking at physical reality in two different ways. And so, how do you combine the two different ways of looking at things? So Andrew says unifying just means that you can describe something in both those regimes, i.e. paradigms. Quantum field theory tells you how to deal with relativistic quantum particles, yeah. But there's still problems. It's when you combine gravity to it and so forth. Does anyone here doubt or object to anything that involved quantum mechanics? Yeah, we're dissidents, our group here, John Chappell, Natural Philosophy. We're dissidents, and we got complaints with quantum mechanics and relativity. So, but the sessions I'm doing, I'm mainly complaining about relativity. So it would be in that different sort of sessions to go on to address the issues of quantum mechanics. Andrew says, I think a few people here are super determinists. Well, maybe. I think what was the inconsistent fact of correlation of the ideas? Well, Hammond is pointing out he thinks it's space-time. The idea of space-time is making it difficult to unify these two different things, relativity and quantum physics. And she says not much quantum field theory came out in the 1930s, so pretty soon after the foundation quantum mechanics and special relativity were established. Yeah. So yeah, that was special relativity in 1905 and quantum mechanics about the 1920s, and then they got to the issue of trying to combine them, and people started complaining they weren't combined properly. I think it was Dirac who's tried to form the theory of quantum field theory. Yeah. Yeah. Andrew says quantum field theory is also important for astrophysics, condensed matter physics, particle physics, and quantum computing. Yeah. Okay. Oh, God. Okay. So, Franklin says, I don't think either of these videos address the question of space-time. Well, this is sort of the second session on space-time. And the first session, I was hoping to deal with it. Space-time as being explained as the idea that came from Minkowski. It was an idea that added to special relativity. But if that's not clear, I'm sorry. It's sort of like accepting the idea of space-time and then complaining about it in this particular session. So next one by Franklin. You don't get rid of space-time on the basis that it is hard to measure, which seems to be the point of the last video. Yeah, it's hard to measure on the Planck scale. And sort of the theories they have don't address what's happening at the Planck scale, and so that's what they're trying to unify things on. Andrew says no one is getting rid of space-time because it's unified in quantum field theory and incredibly important to nuclear physics. I think Hammond was trying to say we should bring out something better because the theories aren't really properly unified of quantum mechanics and relativity. It can work as a sort of approximation, but then the theory starts breaking down. Yeah, so Franklin says Roger just showed two videos, one of which asked if gravity a force, but doesn't answer it. Well, I think in Sabine's point of view, gravity is space-time curvature. It's in the context of Newtonian physics that gravity is a force. So I think Sabine is pointing out that relativity isn't treating gravity in the same way. Did Einstein ever start to disagree with the space-time continuum? Well, Einstein took several different approaches to try to unify physics by coming up with a unified theory. So that would be an issue to look at for some other session, but that's too far advanced for this one. Clive asks, is it possible to send a longer document, A4 for example? There's a great deal of literature on this sort of thing, and I'm just pointing out what Sabine was thinking and what Hamid was thinking, and they got videos on that, and they got a lot more videos and papers and so forth on that. So this one, Franklin. Einstein himself says he stopped understanding himself once the mathematicians invented relativity. Yeah, so the mathematicians, when they got space-time, they did a lot of strange things with it. So maybe that's when he stopped understanding the mathematics. Yeah. In theoretical physics, quantum field theory is a theoretical framework that combines classical field theory, special relativity, and quantum mechanics. Yeah, but there's also general relativity, which is sort of like dealing with gravity. So, Franklin says energy is just the quantity of matter in motion. So in that way, it is very visible. Whenever you are seeing something in motion, you are witnessing energy. Yeah, that'd be kinetic energy. Yeah, Andrew says you literally use the space-time interval in quantum field theory to compare results from different experiments and different models. So, as Franklin says, Einstein accepted an ether as a means of transmitting force, and Einstein is usually interpreted as 1905 discarding ether, and then in 1920 he seems to be bringing back the ether. So the mainstream runs into trouble then of deciding who to go with, Einstein 1905 or Einstein 1920, and the mainstream seems to go with Einstein 1905. But anyway, carrying on, Franklin says, but then said the really stupid assertion that it didn't consist of particles that could be tracked. Yeah, this is complete contradiction. Yeah, so he's arguing about the ether. Yeah, it's probably you can argue about ether for ages. Yeah. Robert points out Einstein was not clear on whether his ether was at rest or moving. Yeah, Einstein's unclear on a lot of things when you read him. How does space-time prevent the unification of relativity and quantum mechanics, though? So space-time is part of relativity, and using the relativity principle, constancy of light speed, the equivalence principle, and so forth. And quantum mechanics is the ideas of Heisenberg uncertainty principle, wave particle duality, and other things. So it's how do you combine all these different concepts together to create a unified theory? And Hamid's pointing out, well, discard space-time and the unification might be a bit easier. So, Andrew says you have to be careful defining energy as matter in motion, because that begs the question as to what you're defining as matter. Yeah, matter is substance. And what is substance? Substance is particles. And what particles? Particles are wave packets. What are waves? It's just endless. The questioning goes on and on and on from that point of view. Okay. So, John says, unifying begins, in my opinion, with considering space-time as a quantum ether such as vacuum energy. Yeah, maybe. I think some people will propose that. So, Andrew says these videos are a bit of mental masturbation in the sense that no one that watches them will have their minds changed. Well, I think physics is just about arguing. People have different opinions, and it's just endless arguing. Then, if you believe in physics, you keep believing. If you don't, you won't change. But people in physics, people have different opinions, and they just end up arguing. So some people believe in relativity, some people don't. Some people believe in quantum mechanics, some people don't. It's just arguing. Well, where does special relativity break down nuclear physics? Well, as I think in an earlier session I pointed out, the problem is different people say different things about special relativity. And I had one session where I pointed out some people were saying relativistic mass exists, and other people saying it doesn't exist. And they're both claiming that is special relativity. So special relativity becomes ambiguous as people say that's relativistic mass exists, others say it doesn't. It just becomes into a mess, just a mess of people saying different things. Just okay. So Franklin says to Andrew, can you mention one thing in nuclear physics which relies on the space-time concept in order to actually work? Pass. What? Oh. So how exactly to define space-time? Well, there are three dimensions of space, and then it's treating time as the fourth dimension. So you're dealing with 4-dimensional space-time. Yeah. Other than time is the fourth dimension. Yeah, that's it. The treating time is the fourth dimension. So I think this is people discussing things among themselves. And John is saying to Andrew, energy is a physical observable question mark. By what instrument? Question mark. Don't we measure mass, distance, etc. Then calculate. Oh, well. Next. So this is cross section. This aspect cross section. We're not dealing with that. So. Yeah. Yeah, so not dealing with scintillators and so forth. So it's just people discussing things among themselves. Yeah. So showing some videos, and people have gone off at a tangent now to discuss other things. So Frank is saying to Andrew, you use just special relativity to determine the cross section, Frank. Yeah, so the videos weren't dealing with cross section. So. What's this? Andrew says, Roger, you claim special relativity breaks down in nuclear physics, but can't give an example. Don't know what you mean by that. It was Hammond was pointing out there was problems at the Planck scale, and I pointed out when people deal with special relativity, they believe different things. Some people will believe there's relativistic mass, and some people will believe there isn't. So when they're talking about experiments such as in nuclear physics, they're not all believing the same thing. When they say they claim they believe in special relativity just becomes some vague words. Which Franklin says, my point is that Andrew may be using space-time to mean anything, using any concept of relativity. I don't think any actual experimental results is calculated from any space-time formula. So I don't know what Andrew's thinking about that. So Andrew says, space-time warpage tells you how the decays change in your reference frame, which is proportional to the cross-section. Yeah, so, but not really addressing cross-section. What's yeah, I think that's addressed to Andrew. So Andrew says, although space-time warping is a sloppy term which is ill-defined, a lot of things in relativity are ill-defined. It's just vague ideas. Oh well. So is space-time that allegedly causes time dilation with gravity? I think you're writing down mathematical formulas, and so it's difficult to say what causes what. From my view, yeah. Franklin says space-time is being used to justify the force of gravity. It's baseline curvature is supposed to be gravity in general relativity. And some people think it's space-time curvature instead of a force of gravity. But maybe it's two different things talked about in different ways. And in fact, it carries on. If you have something that relies on space-time, then it should have something to do with gravity and acceleration. Yeah, the equivalence principle. So Franklin says, another space-time concept you mentioned, Chekhov angle, which is just the shock wave angle, which is also present in sound waves. It doesn't have anything to do with space-time. Right, I think I've got to the end of the comments then. I can open up now to anybody else. Anybody want to hold their hand up? No. Oh, Dennis. Well done, Dennis. You're muted, Dennis. So let's see if I can unmute you. Unmute yourself. Yeah. Hi. Hi,
Can you
Dennis.
hear me now?
Yep. Hi. Good. Can hear you, Dennis.
Okay. Ron Hatch, who was the last of the big GPS guys,
Yeah.
published a paper in 2007 in Physics Essays, A New Theory of Gravity, where he pointed out that black holes don't exist. There are conceptions and misinterpretations of the Hubble telescope and so on. And he also pointed out that there were no gravitational waves experimentally, and he went into some details to why not. This paper is not a hard read, as you might think. There'd be tensors with all sorts of indices and so on. If you want to get an unbiased view of gravity based on the same guy who made the GPS so incredibly accurate, that'd be a good paper to get. It's Physics Essays, 2007, Ronald Ray Hatch, and it's A New Theory of Gravity and some other words following.
Yeah. Thank you. Yeah, black holes. I don't think we're really dealing with, but the mainstream's sort of gone with the idea of black holes, and various disciplines come up with other explanations for supermassive objects. So
the quantum field theory is useful in practice, but it limits the advance of science because it tries to include everything in it when we don't know everything. It's a little bit arrogant. For example, Morton F. Spears has an electrostatic theory of gravity, which points out that the reason that you can't compute the gravitational constant of Newton to enough decimal places as you should, that's because the permittivity of the matter in the universe counts too, as well as, that is, the dielectric constant counts too, as well as the usual Newtonian parameters of distance and so on, and mass and so on. And how are you going to fit that into a quantum field theory, which includes the equivalence principle, when it shows that the equivalence principle is false? Also, Alexander Dmitriev, a Russian physicist, has published some papers lately doing experiments which show that the equivalence principle fails too. And they're short papers, they're not hard to understand, they're experimental rather than theoretical. And so it's Alexander Dmitriev.
Yeah, I think the equivalence principle fails, but it can work as a good approximation most of the time.
It's useful sometimes as an approximation.
Yeah, so if you could think in terms of Newtonian physics, you've got a gravitational force, but really you should also have a force opposing that, an anti-gravitational force, and the equivalence principle, as it's usually formed, doesn't really deal with that.
No.
Okay. Hey, thank you. Cheers. But space-time is one of the things that confuses things. Okay. Thank you. Cheers. Okay. Cheers. Finished?
Yeah.
But bye then. Thank you. Bye. Okay. Next. Any other sucker? Anybody else wants to say anything? Just Franklin, do you want to say anything? Hi. Hello. Do you want to say anything? Big guy. Hello.
Hello, Roger.
Hi, Franklin.
So I was kind of hoping on a a more substantive discussion on your topic, which is, should space-time be just discarded, right? Which I
it's
think
just the ideas, isn't it?
I think that that was a compelling topic here, and so far I'm not really seeing any substantive information one way or the other. Sabine's video was just the mainstream mouthpiece for blah blah blah. Accept this. It force is not, gravity is not a force, and we do it by putting rubber sheets, which is, like I keep on saying, is the most ridiculous analogy ever, because obviously the only reason why the ball rolls down the rubber sheet is because they're using the force of gravity. But you can't define the force of gravity even in an intuitive sense by
I think
gravity.
in one of her videos that she does point out that it's not a very good analogy or metaphor, but it's what they use, that space-time as curved, and so you can't really draw a picture of 4 dimensions being curved in our 3-dimensional world.
It's worse than that, because the problem is, if it's curved, then I can understand how you could justify, like, the moon going in a circular orbit around the Earth, because it's moving, and you're just thinking, well, space is quote unquote curved, so the moon thinks it's going in a straight inertial line, but because space is curved, then it's just following what it thinks is a special. But because space is curved, it's going around. And so that can make sense. But what does not make sense is that if you took the moon and you just stopped it, right? So let's suppose space is curved like that. That means that, if you have to push the moon in order for it to keep following that curve. But if the moon is just stopped and space is curved, then it should just stay there. Right? It only affects the trajectory if it's curved. It's not going to then cause it to take a completely different direction, like we know it will, which is going to go crash straight down into the Earth, accelerating the whole way. Right? See, that's a fundamental problem with curved space, and that is forces create accelerations. Right? It's not that they just change direction, which is what any kind of curved space would do. I mean, no matter how you distort space, it can only affect moving objects that are moving through it. It can't just.
Well, the object is supposed to distort space-time as well. So,
but now space-time is supposed to, somehow create spontaneous acceleration, right? I have my pen; it's stationary. If space-time were true, when I let go, it just stay there. But it doesn't, right? What caused it to suddenly accelerate?
Space-time by the Earth is big enough to.
And the other things, like what were mentioned, which was that there is no gravity, but rather it's the floor pushing up on you at an accelerating 9.8 meters per second, which is causing your perceived force that we observe as weight, right? And that also seems to be an equally absurd idea. Some people have taken that to mean literally that the Earth, the outer surface of the Earth, is expanding outward at 9.8 meters per second. Literally, that this I will call that the exploding Earth expanding, not just but expanding, but explosively.
If the Earth is flat, then we're all moving upwards, and there's no underside. That would make a lot more sense. But being a sphere, then the whole surface of the sphere moving outwards, it's the exploding sphere, isn't it?
Yes. Well, I just don't see how any sensible person could ever accept any of these concepts. Things like gravity is not a force. And it's like, no, that's obviously wrong. Gravity is obviously a force. It's something which can take matter and accelerate it. The only things that can do that are actual forces. But the thing is, I think people have become so frustrated at their inability to explain this that they're willing to go out on, really, really far limbs and speculate that if it's not a force, then it has to be something else. And what else could it be? Well, it could be space-time distortion, which is just throwing the baby out with the bathwater. I mean, the other problem is that we have other forces. We have, like, say, the electromagnetic force. We have, say, the magnetic force. And those things also seem to act like gravity. I'll see, like, a positive charge and negative charge. I take two ping pong balls, and I charge them up oppositely, and they will attract each other. So is that a force, or I could just easily say, oh, that must be another, space time, whatever
Einstein,
thing it is.
Einstein, in his unified field theory quest, he was trying to unify everything. Yeah. Sorry, a minute. What were you saying? No.
But
sorry, interruption there. Sorry, wife.
Yeah, well, I think the whole thing is just absurd. This is why I'm challenging Andrew. I know, and maybe he has a point. Maybe space time is used somewhere, but but I'm still not really seeing that. I'd have to see an actual calculation of it actually taking into account, like, it would have to have at least seconds in it, right, as a dimension. But all the things he mentioned seem to have to do nothing but with special relativity, right, and time dilation effects. All of that stuff, that's 1905 stuff, nothing to do with space-time or gravity or the distortion of space.
But space-time got added to it. 1905 paper, Einstein, no mention of space-time. Then Minkowski brings it in, I think, 1908, and that gets added to relativity. But one of the things I get, bringing back to your thing about electromagnetic force, well, gravitational forces is curvature of space-time. Surely electromagnetic force would be curvature of space-time as well. So when they're talking about light, there should be an electromagnetic force of it. So when the special relativity is talking about light in a flat space-time, that must be wrong. But they sort of like just blunder on all the time with these things.
Well, I mean, I think they are entirely wrong. I mean, my own theories say that, gravity is a force. In fact, it's the electromagnetic force.
Yeah.
I think, it's a very simple application.
Yeah. Yeah, so
you take the Earth,
physics is a mess.
That positive charge attracts every single neutral particle around it. And that's it, right? I don't have to break out rubber sheets. I just have to say, electron attracts proton, right?
Yeah.
Or proton by itself attracts neutrons. It's and it is a force. It's not. It's. We have the equivalence principle, but I think at most that is a coincidence. That acceleration forces can be seen as similar to actual acceleration forces, such as the electromagnetism, and but they should not be considered exactly the same, is what I would say. I'm thinking that this is a pure example of physics just running off the rails, right? You're so desperate to come up with some answer to what is gravity, is that you're clearly making stuff up that just doesn't make any sense at all.
But if you go back to Einstein, 1919, he becomes famous, and Eddington, all that, they say, relativity, general relativity is confirmed by the bending of starlight. If you sort of discarded all of that and just went back to how Newton's physics was dealing with things, you would still be talking about forces instead of space-time curvature. So it's all the things that Einstein added from 1905 onwards, it's sort of like sent physics in the direction it is for that sort of thing. But then in the 1920s comes along quantum physics. So from the historical point of view, it does look like physics has gone in sort of a major wrong direction by having these two different ways of describing things: Einstein's relativity and quantum physics.
Well, it's not practical.
Yeah.
If you're Elon Musk and you want to defeat the concept of gravity, well, does anything in space-time give you any possible way of engineering your way out of that? And the answer is no. It's like there's nothing you can leverage to alter the curvature of space-time, because it's really entirely circular and ad hoc. But mostly it's ad hoc. That you're basically saying that the force of gravity is due to the force of gravity, is what it ultimately comes down to. And when you have definitions like that, then there's nothing that you can practically engineer in order to defeat the force of gravity.
Yeah.
But if you had an actual answer, like, I say the force of gravity is due to the positive charge sitting on the Earth. And then, as an engineer, you would then go, aha, if that's the case, then all I have to do is charge up my spaceship a positive charge. The positives will repel. I will defeat gravity. And you see that shows that at least that theory leads you to a workable solution for defeating whatever we're perceiving as the force of gravity. So any explanation for the force of gravity, which basically doesn't give you any clue about how to manipulate it, I would say is suspiciously circular and is likely false. So and this whole space-time thing is just reeks of that. It's just
well, some dissidents do criticize Einstein for using circular reasoning. The sort of thinking process is circular. He comes up with these things like thought experiments, and then that's the reason for why he has such and such a principle, and it's all sort of like circular. He wants the speed of light to be constant, and that means that time and space measurements are not constant, but not absolute, but are relative. So it's all sort of like circular. It's sort of like light speed constant, time and space relative. It's sort of like you're in a loop. You're not in a prove something external sort of thing.
Well, it really doesn't explain anything. I mean, ideally, science would like to break some mysterious phenomenon like gravity into some other phenomenon which we think we understand, right?
Yeah.
But oftentimes, the gravity is such a hard nut to crack that people are just resorting into these, I would say, science fiction explanations.
Science fiction is good. It's Star Trek. When they have warp space-time, that's brilliant, because you then travel off to other planets and so forth. So,
yes, I mean, and it's like that's a cool concept. Logically, it may even make sense. But there's not a scrap of
it's
actual
good
science
fantasy
behind it.
It's good fantasy. It's a good bit of fantasy. Star Trek. People like that.
But I think all this space-time stuff, it's about as good as a Star Trek transporter. It's like a nice idea, but it's completely false. But I see Nick is waving here, so maybe we should give him a chance.
Okay, thank you, Franklin. Thank you, Franklin. Next up, Nick. Then we move you up at the stage. Hi, Nick. Welcome.
Hello.
Welcome to this session.
Yes, unfortunately, I had problems with the internet and couldn't sign on, so I missed much, even Andrew's comments, I guess. First of all, I'd like to say I agree 100% with Franklin I saw this explanation of this indented rubber sheet, and that was supposed to explain gravity. But the only reason something going along the rubber sheet would go down is if down was defined by gravity. I mean, if you were in outer space and there was an indented sheet, that wouldn't bother you at all. Just go zooming around. So all the explanations assume that down is where gravity is pulling you.
Yeah.
So they're defining gravity in terms of gravity.
I did point out to Franklin that I think Sabine does point out that is a bad analogy. And I've argued with people who believe in relativity, and often they will accept that is a bad analogy. But what you're talking about is 4 dimensions of space and time being curved, and you can't actually represent that properly because we only see 3 dimensions. So you're trying to represent something which is not really visualizable. There's no actual way of showing it. So it's only a very rough analogy to have that rubber sheet being bent. It's not really like that. Okay.
And you brought up the equivalence principle, and I would just like to mention that the late great Ron Hatch, who was the expert on GPS data, said that not only did the GPS data disprove special relativity, there's the velocity effects on atomic clock rate is not symmetric between 2 observers, it's asymmetric. And doesn't follow the time dilation equation. It follows the Lorentzian clock retardation effect. And also, he said that GPS data disproved the equivalence principle. There are times when there's some, as Franklin correctly said, you can see similarities, but there's no equivalence principle. There are qualitatively different things between the effects of acceleration and being in a gravitational field, and the GPS data confirms that. I'd also like to butt in and make a point of my own. I had a presentation, and I put up the URL of that, at least in the green room chat, where I contended that time not only has no dimensions, but is a purely human psychological construct that has no counterpart in physical reality. Basically, we see change and motion and whatnot, but that's all within 3-dimensional space. And processes have all the properties of time, but these properties unfold within 3-dimensional space. So if anyone wants to look at that as I think it's related to the whole idea of space-time, but time doesn't exist physically, then I spent my 50, 60 years in physics trying to find out a better way for physics to treat time, because there were big problems with how physics treated time. And I didn't read all the philosophers, but the few philosophers I read were just so vague. I knew, it wasn't a really good guide to physics. And after 50 years being quick on the update, it only took me 50 years to suddenly say, hey, it's really proper time. And then I went one step lower. Proper time is the time is the counting of a particular stable process. So that's what the real physical reality is. And time is always, quote unquote, time has always been measured in terms of stable physical processes. So again, I have that URL if anyone wants to take a look at that. But did you have any thought about that view of time?
Yeah, it's a philosophical problem, isn't it? What is time?
And that's what led me to, I think, a more purely physical view of a replacement of the philosophical idea of time with something physically concrete, namely process rate. And again, processes have all of the properties of time, and it just comparing the process rate of one process versus another process. By the way, another thought was that special relativity is supposed to be valid for only inertial frames. And if you have some force accelerating something, then that would not be an inertial frame. But supposedly gravity is the one force where you can be in free fall due to gravity, and allegedly that you're still in an inertial frame. And that was sort of invented to solve some problems with relativity.
Yeah. Do you see the comment by Andrew here? So if Ron Hatch is such a heavyweight in disproving special relativity, why isn't anyone building off of his work?
Well, yeah, there are two replies to that. One is we are building off of his work. There are, a whole lot of people, and some of them in the mainstream. But Andrew, again, I think one of your beliefs in special relativity is that you see that the equations you use, or that they are using, that they think they're using special relativity, seem to work. But in Ron Hatch's world, GPS, the data that's qualitatively does not match relativity. So one of the problems, I asked him the same question, and one of the real heavyweights was Brad, I'm forgetting his last name, who is really the founder of GPS, main mover. He didn't want to shake up or challenge physics academia. That would be a very bad move. And in some cases, he didn't want to shake up things politically. There's a lot of politics involved in backing up physics academia. But a lot of when back in the days, maybe 10 years ago or so, we used to have people come into the CNPS who were doing real physical things, giving us presentations, and time again they would say, we don't use special relativity because it doesn't work. So the people who are outside of academia and have to do things that really work, like GPS, they don't use special relativity.
Cynthia.
So there were two worlds: the academic, purist, theoretical, and the people who want to get things done. And even in the academia world, and things like accelerators, which are what convince you that special relativity is correct. You use equations, but the physical interpretation is anti-special relativity. Now, the person who runs the SLAC accelerator out of Stanford discusses this. He says, first thing we have to do is unteach the PhDs who come into our program special relativity and, set them straight as to what's really happening physically. So it's a good question.
Yeah, there's also Cynthia Whitney. She was doing a thesis on relativity, and she found that relativity didn't work. And her mentor, it doesn't matter. just carry on. And so she got discouraged with physics. So there's lots of people who find out that relativity doesn't really work.
Sometimes you can use equations that look like special relativity, and they will give you the right numerical answer. But if you follow through, what is the physical model you're actually using? You find the one you're using is not the special relativity model, which is if you follow it properly, it's a symmetric just observed. But a lot of these effects are physical, like clock retardation. That's the Lorentzian physical preferred frame point of view. In GPS, the preferred frame is the ECI frame. And there is a preferred frame for the accelerators too.
And these people who do experiments and so forth, and they say, they've proven special relativity, but they've all got different opinions of what special relativity is. Some believe it's got relativistic mass, and some believe it doesn't have relativistic mass. And then some believe it's got preferred frame, and some believe it doesn't. So they don't all believe in the same thing when they say they believe in special relativity. They believe in the different things.
Well, thank you very much, Roger, for this series. Very important.
Yeah. So I'm highlighting the problems, and in this one, I've highlighted that you can consider people in the mainstream who are rejecting part of relativity from the theoretical point of view. They're thinking that space-time causes a problem, because Hamed was pointing out that not only he believes it, but other people he's working with think space-time is a problem. So thank you, Nick.
Maybe Franklin can post that my URL to the my discussion of time if anyone's interested.
Okay, I got Dennis with his hand up now, so thank you. Bye then. Cheers. Thank you. Bye. You move. Bye. Dennis at the stage. Hi, Dennis.
Hi. I'm 81, so I remember in the days when the GPS program was starting up, there were a number of articles published by physicists who said that these engineers don't understand special relativity. What they're trying to do is to synchronize clocks in the Earth-Moon and later on in the inner planets. Can't be done. It follows from special relativity. That's impossible, and if they only knew about special relativity, they wouldn't engage in such a project. Well, then it turned out that the GPS worked. So what did they do? Did they apologize and promise to look into it more carefully? No. They just shut up. There was not a word from them. And then after Ron Hatch died a few years ago, then they started publishing papers saying that the whole reason special relativity is right is because the GPS works. In other words, the working of the GPS proves special relativity is correct. So the problem is what I call a cancel culture. Children, is they try to cancel each other, and so no one will talk to them, and to the person who was canceled, no one will talk to them on the internet or on Facebook or all the other media, social media, and people think that originated with the kids, but it didn't. It originated with the physicists during World War II, especially the Manhattan Project. Since it was so secret, anyone who mentioned anything about it, especially anything critical about it, was canceled, disciplined, and so on. And then it spread down through the academia till it finally got to the kids, but the kids were not sophisticated enough to effectively deny what they admitted that they were cancel culture people. Whereas the academic people, especially in physics, wouldn't admit that, even though it was true. They were sophisticated enough to talk people out of it, to deny it. People believe them.
Okay. Cheers. I'm getting distracted by looking at some of the comments here. I don't know if I should deal with them. It seems to be going off at a bit of a tangent in the comments.
Well, do you have any comments for me to discuss?
Andrew was still not believing in the what Ron Hatch said about GPS, I think.
Well, he seems to be a true believer.
Who? Andrew.
Yeah, I'm referring to the book, The True Believer by Eric Hoffer. I think you ought to read that book.
Yeah. I think we've got a bit of feedback now. Okay. Thank you, Dennis.
Can I say a little more? I wasn't through.
Go on, carry on then, yeah. Say some more.
Okay. So nowadays, anyone who says anything in academia who's a physicist, anyone who, especially big academia, anyone who says anything against the main physical paradigms that are currently in use, even though they're antiquated, it's canceled. Meaning that if he hasn't got tenure, he will be denied tenure. If he does have tenure, they'll either fire him anyway, or if they're worried about legal action, make his life miserable to the point where he'll quit. And so that's why you don't hear much against the physical paradigms of the mainstream physical elite, because they have power to, well, as I say, cancel you. And that's why the GPS people who do not use general relativity or special relativity, they do not admit to that publicly, because academia is powerful, and companies that employ these people who do not use special relativity don't want that kind of trouble. They're out to make money, and which is pretty obvious, I guess. But to argue against the main physical paradigms of the physics elite is a good way to lose your career and end up working in a grocery store as a janitor or something.
I think the main video I showed, the half-an-hour one, Professor Hamed, he is mainstream, and he's not coming out and openly admitting that Einstein's relativity is wrong. He's just trying to amend a small part of it, namely about space-time.
Yeah, he's just saying that there are still problems, but they're subtle ones, and he's not advocating changing anything other. Well, he did argue that maybe if we got rid of space-time and replaced it by something else, these problems might go away.
Yeah. He's not coming out saying, oh, Einstein's relativity is all wrong. He's not saying that. He's coming out and just trying to alter a little bit of it.
Yeah, and replace it with something that's probably almost the same, but just slightly different. Yeah. The idea that there could be gravity could be an electrostatic effect.
Yeah.
It would horrify him, I'm sure.
Yeah, I don't think he's saying that. I think Hamed's not saying that. He's just coming out with this bit about the space-time. It seems to be its concentration.
Yeah,
So you get away with altering just a little bit of it, but if you try to come out and say, "Oh, it's all wrong, it's all nonsense," then that's when you get banned. You don't get your tenure as a professor or your research grants given to you if you're going to say it's all wrong. That's the problem with it.
Yeah.
Well, they tinker away with it. Some people say one thing, and other people say something else, and so it sort of like blunders along. Yeah, but space-time has been added to relativity, and it has made things more confusing. I think Vladimir put his hand up, so yeah, he's put his hand up. So thank you, Dennis. Go to the next one. Come on, Vladimir. Okay, Vladimir. Welcome. Hi, thank you. Your microphone's not working. You're muted. I can't hear. You muted. You're muted. Sorry, Vladimir, you're muted. Can you hear me? I can't hear you. Not working. Don't know. No, can't hear you, Vladimir. I can't hear you. Sorry, I can't hear you. Can you hear me? I can't hear you. You're not coming through. Vladimir, you're not working. Okay. Okay. Vladimir's still talking away and I can't hear anything. Can anybody hear him? Can anybody hear him? No. Sorry. So sorry, Vladimir. I can't hear you. I don't think anybody else can hear you. Your microphone doesn't seem to be working. So I don't know. So I don't know what's wrong there. According to what I'm looking at here, your microphone should be working, but it's not. I can't hear you. Okay. Can't hear you. So I can't hear you. Can't hear you. Sorry, I can't hear you, Vladimir. There's something gone wrong. Okay. No good. Sorry. So I think I'll end the session here. Sorry. So thank you, everybody. I think I covered most of it. We have touched on the issue of space-time, but as Franklin likes to point out, we haven't got enough detail about it. But it's the idea of adding space-time to relativity came after Einstein, and then maybe it causes a problem when you try to combine it with the other ideas from quantum physics. That was basically what I was trying to point out. So thank you, everybody, and I'm ending the session now. Thank you, and goodbye. End of another exciting anti-relativity talk. Cheers. Bye.